Okay, so now we're going to take a look and see how the stoichiometry of an equation actually affects the rate of the reaction, how we actually write that expression. So remember, stoichiometry really all hinges on having a balanced chemical equation. And specifically, what we're going to be looking at in this balanced chemical equation, right, are the coefficients. Which are just a small whole numbers that we place to balance the equation. So let's start off with a simple example before we go into an actual real life example. So let's think about an equation or reaction where A turns into B, but it's not a straight one-to-one reaction. A actually turns into 2B. So as we know, we can write the rate of this reaction as follows. We know the rate is equal to the change in the concentration of A over the change in time. And because A is a reactant, we can put a negative sign there to account for that. We can also write the rate of the reaction with respect to B, so the change in the concentration of B over the change in time. And it's a positive value because B is a product, its concentration is going to increase. Now, what you'll notice though um, is that B is actually formed at twice the rate that A is used up, right? So A here, remember, when you don't see a coefficient, 1 is understood to be there. So in order to ensure that the rate of the reaction is the same, regardless of what species we monitor, which species we measure, I'm sorry, to monitor the reaction progress, we actually have to take into account that coefficient. So what we would say is it would be 1/2 of, we can just incorporate that in here, if you want to keep it separate, doesn't really matter if multiplying. We put 1 over 2, and then 2 is going to be my coefficient, right? And in that way, I'm treating both of them equally so that I avoid any ambiguity when it comes to reporting the rate of disappearance or appearance of a specific chemical species in this particular example. So we do need to account for the stoichiometry when we write those rate expressions. And in this simple example here, we were just putting 1 over whatever that coefficient is to account for that. So if you have a generic equation now, something like this, let me rewrite this over here. So we have the lowercase a is the coefficient, and then uppercase a is the whatever that reactant is, reacting with B, lowercase b is the coefficient, uppercase B is the other reactant, to produce lowercase c, that's the coefficient, uppercase c is the product, and then lowercase d is the coefficient for uppercase d. So we can write the rate of this now with respect to all of these chemical species, right? So in the example, when we go back to the right side here, these two rates are equal to each other, right? So I can say then that the rate is equal to negative, and then let me say delta A over delta T, and that's equal to 1 over 2 times delta B over delta T. Okay, and to be more specific here, completely correct, I can say negative now, and I'm going to put 1 over 1 because 1 is my coefficient that I put in here. Obviously, 1 over 1 is 1, but so I can eliminate that fraction, but just to show you how to write it, that's what we're going to do. So we can expand that, we can apply that generally then for our much larger equation here on the left side. So I can say the rate with respect to A would be a negative sign, 1 over lowercase a times delta, change in A, over delta T. Okay, so that's for this. And that's also equal to negative, because we're looking at B now, 1 over lowercase b times delta, concentration of B, over delta T, in time. And that's also equal to now the product. So the product then would be a positive. So it'll just be 1 over lowercase c times delta changing concentration of C over delta T, and then that's the same. That's equal to 1 over lowercase d times delta D over delta T. Okay, so that is how you can express the rate of the reaction with respect to all of the reactants or all of the products while incorporating the stoichiometry. And again, the stoichiometry is just the coefficients that we use to balance the equation. So for example, if we have, let's do a couple different ones down here. So let's say I have item C or item C. I can write that rate as being equal to now with respect to the ammonia, the NH3. So that's a reactant, so it's going to be negative. Then we put 1 over the coefficient, which is 4, and times delta change in the concentration of ammonia over in time. And that's the same as we look at the oxygen now. That's a reactant, so it's going to be negative 1 over the coefficient is 5, times delta change in the concentration of O2 over the change in time, and then that's also equal to how we get to the product. So it's a positive value 1 over the coefficient for NO, 4 delta creation of NO over delta T, and that's equal to now the H2O. We have a product, so it's a positive value 1 over the coefficient, which is 6 delta H2O over delta T. Right, so that's the option C that we have. So as long as you have your balanced equation, right, and that may seem obvious or straightforward, but oftentimes students don't check that the equation is balanced. You need to make sure that you have a balanced equation, and that's true for any reaction that you're working with. Then you can write the rate equation for the rate with respect to any of the reactants or products while incorporating the stoichiometry. Okay, so let's take a look and see how we can apply that to a specific example now to actually do some calculations. Let's consider the reaction. We have 4NO2 reacting with O2 to produce 2N2O5. So double check, you always want to double check that this equation is balanced. So we have to use an equation. It's just good practice to do this. And let's see, we have 4 N's, got 4 N's here. We have 4 times 2, 8, plus 2 is 10 O's, 2 times 5, 10 O's. Okay, so that's our balanced equation. It says at a particular time during the reaction, nitrogen dioxide is being consumed at the rate 0.00130 molar per second. And then it says at what rate is molecular oxygen being consumed, and then B, at what rate is dinitrogen pentoxide being produced. So first of all, nitrogen dioxide, that's the NO2, molecular oxygen, that's O2, and then dinitrogen pentoxide, that's N2O5, right? So we know what species we're looking at or that we're trying to relate in this equation. So we need to determine rates. So let's probably start off with writing the rate equations for these. So we know that the rate, according to what we just learned from this equation, would be negative 1 over 4 times delta NO2 over delta T, and that's equal to negative 1 over 1, and that would be delta O2 over delta T, and that's also equal to now for the product, the N2O5, right? That would be positive now, 1 over coefficient there is 2, delta N2O5, nitrogen pentoxide over delta T. Right, so we have our rate equation written with respect to each of the reactants and products. And then we're told that the nitrogen dioxide the NO2 is being consumed at a rate of 0.00130 molar per second, right? So that tells us then we're given this particular piece of information, the rate of consumption of the NO2. So we have the delta NO2 over delta T is 0.00130 molar per second. And because it's being consumed, we have to put our little negative sign in there. Right? That tells us it's being used up. So we know what this is, and this is probably the most challenging part of this question, is to actually express this piece of information in a way that is going to be useful to you. So what is it actually equal to in the problem? How we can relate it to the rate equation? Well, it's the delta NO2 over delta T, right? So that's the rate at which it's being consumed. So that is the equal to now this expression here is this part of it. So we can take this and we can substitute it into that part of the expression. So that can go in right here. So we can see now the rate is equal to -1/4. And then this entire thing goes in. This is -0.00130. And then molar per second is our unit. Okay, so if we substitute that, or we did substitute it, if we evaluate it in our calculator, let's see what we get. So we have 0.00130, and that's divided by 4. Okay, so that's going to give us 3.5 times 10 to the negative, what is that? 1, 2, 3, 4. And then our unit there is molar per second. Okay, the signs are going to cancel out. Okay, and they should, because as we know, we said before, rates are always going to be positive values. So this rate that we just calculated then is equal to that number that we get is equal to this, which we just found. It is also equal to this. And it is also equal to this, right? Because it's the same. The rate is going to be the same. That value is going to be the same at a constant temperature. We're not really told any information about temperature, so we can assume that it is constant. Okay, so we find the value for the rate to begin with, and then we can go ahead and we can substitute it into the rest of it. So it says at what rate is the molecular oxygen being consumed? So now we can say the rate with respect to the oxygen now is equal to, what do we have here? -1/1 times delta O2 over delta T. Okay, so obviously the 1/1 are going to cancel out. So this ends up being negative delta O2 over delta T. And what is that equal to? Well, that's equal to the thing we just found up here. That's equal to, I'm sorry, we didn't find that. We found the thing right up there, which is 3.25. That's 3.25 times 10 to the negative 4 molar per second, right? There's nothing to solve for here because that actually is what we're trying to determine. So the negative again means that it's being consumed at this particular rate, which is the rate that we found previously. And that's with respect to the molecular oxygen. Part B, at what rate is a dinitrogen pentoxide being produced? Okay, so if we look at B now, again, the rate there with respect to the N2O5 will be equal to, what do we write up here? 1/2. Delta N2O5 over delta T, right? And that is equal to also 3.25 times 10 to the negative 4 molar per second, right? What I need to solve for in this is just to solve for this part of the expression, right? So if I rearrange my equation and I isolate this on one side, I need to multiply both sides by 2. Well, in other words, take this, take that, multiply it by 2, 2's cancel. So I end up with a left here, delta N2O5, which is what I want to get over delta T, right? That is what I'm trying to determine here, right? The rate at which, being asked the rate at which the nitrogen from compound is being produced, right? That is what that expression means. And I solve the right side of this equation, multiply that by 2. What do I get? 6.50 times 10 to the negative 4 molar per second. Right, so we can solve it that way. So it's not, it may seem complicated when you, if I would just throw this at you with all the different symbols and whatever, it's actually fairly straightforward as long as you have a balanced equation, right? And as long as you know the general technique and how you write these rate equations with respect to each of the reactants and or products while incorporating the stoichiometric coefficients, right? Those are really big words that I just used, but they mean really simple, really simple things. Okay, so it's important that you practice how to do this, and then substituting your values in and just solving for the unknowns. Again, this just boils down to just algebra and then rearranging equations.